Let's implement the two-pole resonator filter in LabVIEW. I have the equations listed in the block diagram. So H of Z would be the two-pole resonator, and then I have some of the helper calculations like the R value and the theta listed as well. I'll begin by creating some front panel controls for the two-pole resonator. Ultimately, we're trying to come up with a sub-VI that can serve as a single sub-VI that processes an input signal according to our center frequency and bandwidth. So additional front panel control that we need is the sampling frequency. I'm going to use a math script node to handle the calculations of the filter coefficients. I'll begin by connecting my front panel controls to the math script inputs. All right, for the first calculation, R will be E, so that's EXP in math script notation. E raised to the minus pi, and pi is a built-in constant, times the bandwidth parameter divided by sampling frequency. Next, let me call the gain on the entire structure simply 1 minus R. Represent that by capital G. All right, we need to form 2R cosine theta, and that corresponds to the A1 coefficient. Recall that all of the coefficients of the denominator are the A coefficients. They start with A0, which is on the far left. There is 1. A1 would be the next one. So I'm simply doing a direct translation of minus 2 times R times cosine 2 times pi, because theta is 2 pi times the center frequency divided by the sampling frequency. A2 is my next coefficient, and that's R squared. The finished A vector then is 1, that's A0, and then A1 and A2. It's a second order structure, a so-called two-pole resonator, so we're done at that point. The B coefficients are associated with our numerator, and since the gain multiplies both of the numerator coefficients, I'll just write that out as front. So it's G times, and I'll form a vector, which is the B0 coefficient, 1. There is no Z to the minus 1 term, so B1 is 0. And then we have minus R for B2. All right, I'll create some connector terminals on the output side for the math script node. We need the vector A and the vector B. Now when you first place these, they default to scalar outputs, so we need to choose the 1D array style output for each of these. So we've completed our calculation for the coefficients, and we're ready to send those to the filter structure. So I'm looking for the IIR filter, and it's specifically the version that accepts the A and B coefficients directly. Reverse coefficients, that's A, and the forward coefficients are equivalent to B. Give a little room for the input here, and there's the output of the filter. Let me create a front panel control and a front panel indicator that are associated with our signal path. Actually, I need to come back and call that X. Typically, we'd call the input X and the output Y. Let's take care of that now. There we go. Let me move our signal related front panel elements together. And to wrap things up, let's take care of the front or the connector pane. Connector pane. Getting ready to have this be available as a sub VI. So I have my signal flowing into and out of the top of the icon, and then I have my parameters underneath that. Now perhaps if you had a little more time, you could make kind of a little more fancy icon for this, maybe a little bell-shaped curve to represent the frequency response of the two-pole resonator, which is a bandpass type response. For now, let me just call this the two-pole res. I'll add just a bit more documentation here. And when you save this VI, it's ready to go as a sub VI that you can then drop into another design.